Hello everyone, welcome to Thermofluids Lab. On this video, we're going to talk about Brayton cycle. A Brayton cycle is basically the working cycle of a gas turbine or a jet engine. It was first introduced by George Brayton back in 1872. The basic components of a Brayton cycle are a compressor, a turbine, and heat exchangers. You can see on the figure on the right, it shows an open feed Brayton cycle system or gas turbine system. You'd have fresh air going into the compressor and you're going to compress the air, it increases its pressure, you're going to feed it to a combustion chamber where you'd inject fuel and have combustion. The exhaust of from the combustion chamber would be used to rotate a turbine. The turbine would in turn produce work and generate electricity if you're using a gas turbine, um, or create thrust if it's a jet engine, and also sometimes it is used to rotate the compressor as well. So you would use the turbine work to power the compressor and do external other works. And then the exhaust gas will be fed to the environment or the atmosphere. Braking cycles are mainly either an open system or a closed system. An open system braking cycle basically involves combustion chambers. So generally jet engines use open system Brayton cycle, or gas turbine power plants that uh, do not use a closed feed working fluid uses an open system. The closed system Brayton cycle are basically closed cycle gas turbine power plants where you'd have a working fluid in a closed loop. You'd basically have two heat exchangers. One would be used to increase the temperature of the working fluid to have work done on the turbine, and you'd have another heat exchanger that would reject the heat after the work has been done on the turbine and then uh, flow it to the compressor. A reverse Brayton cycle is basically a closed Brayton cycle that works in reverse. Instead of using high temperature fluid to generate work, you'd be starting from going in reverse from the turbine. So you'd have, instead of work using the fluid to work being done on the turbine, you'd have the fluid to reject heat out from the system. Basic examples are refrigeration and air conditioning cycles. There are other Brayton cycles like inverted Brayton cycle, solar Brayton cycles, and hybrid Brayton cycles. Let's talk about Brayton cycle operation. You could see on the picture that we have an open feed Brayton cycle and its working diagrams on a pressure versus volume and a temperature versus entropy plot. Now the ideal cycle says that on the compressor from 1 to 2 you have isentropic compression. Then on the combustion chamber 2 to 3 you'd have an isobaric heat addition. 3 to 4 would be your isentropic expansion, where you'd have work down on your turbine. And then 4 to 1 would be your isobaric heat rejection to the atmosphere. Now if you know about the laws of thermodynamics, or the second law of thermodynamics, you know about irreversibilities. Due to irreversibilities, it is highly unlikely that you'd have isentropic compression or isentropic expansion in the compressor and the turbine. Instead, on the actual cycle, those two are adiabatic compression and adiabatic expansion. So adiabatic compression means no heat transfer occurs during the compression, and adiabatic expansion means no heat transfer occurs during the turbine work. Similar to Rankine cycle, we're also interested in finding out the efficiency of the Brayton cycle. Now, similarly, we need to know the individual work done or energy output of each of the components. Now, the heat addition to the system at the combustion chamber would be equal to mCp delta T. The delta T would be the temperature at the outlet of the combustion chamber minus the temperature at the inlet of the combustion chamber. The work done by the compressor would be the change in enthalpy between the fluid from end of the compressor or exit of the compressor to the inlet of the compressor. Similarly, the work done in turbine can be found out by the enthalpy difference of the working fluid between the exit and inlet of the turbine. The heat rejection or Q out can simply be found out by mCp T4 minus T1. Now the efficiency of the system would be equal to net work done by heat input, which is basically equal to work done by turbine minus the work done by compressor divided by heat input, or 1 minus heat out divided by heat in. That would be all for this lecture. If you have any questions, feel free to ask me during the class lecture. Thank you.